All right, Math 136 students, this is the final exam part 2. The last few problems, I had a battery shortage on my laptop, so we're going to finish these up. So it says, number 15 says, given f of x equals negative x to the third times x minus 5 times x plus 3 squared, find all values of x such that f of x is greater than 0 and all values of x such that f of x is less than 0. Then we want to sketch a graph of f of x. So notice this is asking us when are our y values positive and when are our y values negative. So we're going to be looking at this from the perspective of there's a couple different ways you could do this. You could do a sign chart, or you can use what we know about end behavior and multiplicity. So I'm going to use the end behavior and multiplicities because I find sometimes if you use a sign chart for everything, students forget when are they supposed to use it and when are they not allowed to use it. So there's two things we're going to look at. So end behavior has to do with two things. We need to know the leading coefficient sign, and we need to know if our overall degree of our polynomial, if we were to FOIL it all out, is, and so our two choices here are plus or minus, and we need to know if our degree of our polynomial is even or odd overall. Okay, so the leading coefficient's the easy part. You just have to look at the coefficient out front and see if it's positive or negative. So this is a negative. And then to figure out, if you're already in factored form, to figure out your overall polynomial degree, you just need to think about, if I FOILed all this out, what would be the biggest x power I would get? So you get a 3 here. This is to the first, and it's also to the first here, so that's just going to give us 1x. This is squared, so that's going to give us an x to the second if we FOILed it out. So this is 3 plus 1 plus 2, which is 6. Which is an even number. So here's what we know about end behavior. If your polynomial is even degree overall, that's the highest degree in the polynomial when we're listing it, in order, then we know that our end behaviors are heading in the same direction. So either at the infinities, we're going both to positive infinity or both to negative infinity. If we were odd, our degree of our polynomial was overall an odd for the highest power, then we would be heading in opposite directions. So on one side, our x's are going, to negative infinity, and we don't know if we might be going up to positive infinity for our y's. Well, on the other side, we have to go the opposite way. So we'd have to go to negative infinity for our y's. So the difference between them is that evens are the same direction, and the odd ones are in opposite directions. Now, the even being in the same direction could either be both up or both down. That's what the sign tells us. So the sign tells us if they're both up or both down. So if it's plus, it's like a regular x squared and they're both up. If it's negative, they're both down. So this is going to have end behavior like this. Even means they're both going the same way. Negative means they're both going down. Now, if you were odd, you'd have to be concerned with a positive looks like a normal x cubed, whereas a negative would flip the directions. Now, the other thing is the multiplicities, and that has to do with our zeros of our function and their power, which is their multiplicity on that factor, and then what is the behavior at that x-intercept, or 0. So if we set each of these equal to 0, we'll find our zeros, and I usually like to find them first and then write them in order in my chart. So x to the third, negative x to the third equal to 0 is just going to be 0. X minus 5 equal to 0 is going to be 5. And even though this is squared, it's just writing it twice would give you two of the same answer. So we get a negative 3. So my zeros are negative 3, 0, and 5. The power on the negative 3 was where that factor came from. This is a power of 2. And I do like to write it as a word because I don't want you to think this is an ordered pair. X equals 0 came from the x to the third, so that had a power of 3 on that factor. And x minus 5 gave us the 5, and that had a power of 1. Now, if you have an odd power, you're going to cross the x-axis. If you have an even power, you're going to what we call bounce or touch. I like the word bounce better. You can actually look at it, and it seems like a ball is bouncing. And at both of these, we're going to cross. The only difference between a 1 and a 3 is that at a 1, you cross like a straight line. At a 3, you cross like x to the third. Remember, x to the third kind of looks like that. It's a rough sketch. I'm just overestimating that flat line there, but it has that little bit of a little balancing before it turns up back towards the heading upward, or it could be heading downward. It could do this. So depends on if it's coming from left to right. So that's what we mean by crosses like x to the third. And 5 and 6, 7 and 9, any odd power bigger than 1 will cross like x to the third. Okay, so let's graph this out because that's essentially all we need to do the sketch, and then we'll be able to answer the question, when is f of x greater than 0 and when is f of x less than 0? So we have -3 is one of our x-intercepts, 0 is another one, and +5. At -3, that's our farthest left intercept. We're supposed to be going down forever. Our farthest right x-intercept, we're supposed to also be going down forever. So you want to place your end behaviors first. Then you will follow your chart. So at -3, we're supposed to bounce, which means we do not cross into the positive x values. And we don't know how far down this goes, but we do know that if eventually it's going to head back towards 0. At 0, we're supposed to cross like x cubed. So we kind of make that kind of look like it's got a little x cubed nature going on. And then we come up some unknown amount and then head back towards this, and notice we are supposed to cross like a line at 5. And this is a rough sketch, obviously very rough. We don't know how low or high these valleys and hills get. You need calculus for that. So this is my picture, and then I want to answer the question, when is f of x bigger than 0 and when is f of x less than 0? And this is determined on the x-axis. If I pick an x value, will the graph be below the x-axis or above? So from -infinity to -3, our graph is below the x-axis, so it's going to go in this region. From -3 to 0, we are still below. And we don't include that as one interval because they did not ask us equal to 0, so we can't combine that. They said just less than 0. From 0 to 5, we are above the x-axis. Our y values are positive. And then from 5 to infinity, we are back down below. So there is my number 15. Okay, so moving on to number 16, it says find the quotient if the remainder if 2x to the fourth minus 8x to the third plus 12x minus 17 is divided by 2x squared plus 6. Now, if we had divided this by 2x plus 6, because it would have been an x to the first, then you could have used synthetic division. But you cannot use synthetic division when you're dividing by something that is higher than an x to the first power. So we have to use our friend long division. Now, when I do long division, I put the part I'm dividing by on the outside. I don't so much worry if I'm missing a power here, but I do worry about that on the inside because it's a placeholder. So I have 2x to the fourth minus an 8x to the third. I'm missing x squared, so I'm going to put 0x squared in its place, plus 12x minus 17. First question you ask is, what do you multiply 2x squared by to make 2x to the fourth? And we would need to multiply that by x squared since it already has a 2. That's nice to have that placeholder here now because we know where to line this up. Then whatever we put on top, we multiply it by everything in the front. So this is 2x to the fourth, those should match currently, plus a 6x squared. Now, when you do long division, you always subtract whatever it is you got by multiplying, or you do the opposite. So sometimes it'll be minus here, sometimes it'll be plus, but the key is we're doing the opposite. That cancels this out. This would bring down as a -8 x to the third. This is 0 minus 6, so that's going to be -6x squared, plus 12x comes down, and so does the minus 17. Now I want to ask, what do I multiply 2x squared by to make -8x to the third? So it's going from a positive to a negative, so I need to multiply by a negative, and 2 goes into 8 4 times, and I also need another x. We then take this piece and multiply it by everything out front. So that gives me -8x cubed and a -24x. My next step, remember in long division, is to change the signs because we're subtracting whatever we just done. So minus a negative becomes a plus. That should cancel. And then we are left with -6x squared plus 36x minus 17. Last round, we need, and I know it's last round because I'm going to run out of space on my place values here. I have a constant left. Plus the degrees match, and if we go one smaller, then this x squared will not go into an x to the first. So I need to ask, what does 2x squared need to be multiplied by to make -6x to the second? So that would be a -3, because we already have the x squared. So we'll multiply everything out. That's a -18. We will change our signs. So this becomes plus, plus. And then we're going to do our final line of subtraction. So this cancels. This is 36x plus 1. So the reason this is the remainder now is because you cannot put x squared into something that's x to the first. And this part up here is your quotient. So we have our quotient and our remainder. And you will have blanks, obviously, to fill those in for. Okay, so number 17 is let's find the zeros of a given function. The first thing you should always check, unless they tell you you have to do it by the rational root theorem, is you should check to see if this function can just be worked out by factoring. And if it can, and you don't have any rules, just factor it. So I believe we can try factor by grouping here. And if we pull out an x squared out of the first pair, that leaves me with x plus 2. If we pull a minus 9 out of the second pair, that also leaves me with x plus 2. So this is looking promising. So we have an x plus 2 and an x squared minus 9. Then we would have x plus 2, x minus 3, or plus 3, x minus 3, because that's perfect squares with a difference. So then we just get 3 nice answers. This is -2, -3, and 3. So there are my zeros. Let's look at 18. It may also be factorable. We just need to check. If not, we'll use our rational root theorem. So for this one, we need to try maybe to pull out the x squared first, since there is a GCF. That would leave me with x squared minus 4x minus 45. Let's see, 45's factors are 1 and 45, 3 and 15. 4 does not go, 5 and 9, which that will give me a difference of 4. So f of x is x squared times x. It would be a minus 9 to make a -4 in the middle and a plus 5. So multiplies to -45, adds to -4. X squared does give me a 0. We get x equals 9 and we get x equals -5. So there are my 3 zeros. So these first two are completely factorable. Now, sometimes you will encounter larger polynomials or things that you can't factor, and you need a method for finding the zeros, or at least trying to find the zeros. Sometimes we won't be able to find them all. This usually only works if we can find a potential rational zero from our list that we're going to make, or if someone gives us enough information about some of the zeros. So this is sometimes called P over Q, but our textbook specifically calls it C's over D's. So remember, it is factors of the constant over factors of, so this is C, the leading coefficient, and this is D. So I need to list all my possible factors of 36 and 4 first. So 36, so this is C, this is D. 36 is plus or minus, and I make a parentheses just so I don't have to write plus or minus a million times, plus or minus 1. 2 goes into 36, 3 goes in, 4, 6, 6 is 6 times 6, so 4 times 9, 3 times 12, 2 times 18, and 36 times 1. So there's all the factors of 36. The factors of 4 are a lot shorter, 1, 2, and 4. So then your C over D list, and that's the only thing they want for 19, is all possibilities of C factors over D factors. And every teacher might approach this differently. I just go through and put them all over 1, then I put them all over 2, then I put them all over 4. And I just make sure that if something comes up as an answer we've already written, we don't write it again. So 1 over 1 is 1, 2 over 1 is 2, 3 over 1 is 3, 4 over 1, 6 over 1, 9 over 1. So essentially, anytime you put things over 1, you get your list of C's again. Okay, then we get into putting them over 2. So 1/2 is unique. We haven't seen that one. 2 over 2 is 1. We've already got that guy. 3 over 2 is unique. 4 over 2 would be 2, so we've already got that. 6 over 2 is 3. We've already got that. 9 over 2 is unique. 12 over 2 is 6, which we already have. 18 over 2 is 9, and 36 over 2 is 18. So only new ones we got from putting them over 2 was 1/2, 3/2, and 9/2. Now we're going to put everything over 4. So 1/4 is unique. 2 over 4 is 1/2, which we already have. 3 over 4 is unique. 4 over 4 is 1. 6 over 4 is 3/2, which we already have. 9 over 4 is new. 12 over 4 is 3. We already have it. 18 over 4 is 9/2. We already have that. And 36 over 4 is 9. So all of these, remember, would get a plus or minus on them if we listed them individually. Now, that would be a really hard problem to work through if they asked us to find all the solutions, because you have a lot of factors that you could check. Now, here's how we're going to solve an equation that we can't factor on our own, and we need the P over Q or C over D list to help us try to find a rational root so that we can factor it out. So when we look at this and we're trying to solve it, we're trying to know what x's make this equal to 0. And that means that we're looking for zeros. So the first thing I notice is that if I pull out an x squared and I pull out, there's nothing really in common here, I'm not going to be able to factor this one by grouping. So my first instinct is to make my C over D list. So C here is a 12, D is a 3. So our factors of 12 are 1, 2, 3, 4, 6, and 12. Our factors of 3 are just 1 and 3. So this is my potential rational zero list. Plus or minus 1, 2, 3, 4, 6, 12. That comes from putting everything over 1. And then 1 over 3 is new. 2 over 3 is new. 4 over 3 is new. 6 over 3 is 2, which we already have, and 12 over 3 is 4. So this is my list. Now, we can check these by a couple of different ways. You could just do the remainder factor theorem, which says you plug these numbers into the function to see if it equals 0. And when you find one that works, you then use synthetic division to help you factor it down. Some people don't like to do it that way. Some people just like to jump in and do synthetic division right away. And I'm kind of that nature. So I usually just start out with +1 first, and I make sure no coefficients of x are or terms of x are missing. So this is then write our coefficients: 3, -4, -35, and 12. Remember, in synthetic division, you bring down the first number in the list of coefficients. Then we start multiplying and then adding the columns. This is -36, -36, and this last column right here is your remainder. So this is not 0. So that means that 1 is not a 0 of this equation. Then I usually try -1 immediately next, because I want to know if it's closer to 0 than my +1 was, because that will then lead my kind of trial and error here. So this is 3, -4, -35, and 12. So we bring down the 3, that would be -3. That's -7. That's going to be +7. That's going to be -28. Let me double check that. Yes, and then this would be +28. So this is 40. Also not 0, so this doesn't work. But I noticed that this was closer to 0, -24. So I'm going to stay with a positive value for my next try, and I'm going to try 2. Now, usually if I don't get something to work with this next integer, I will then try sometimes a fraction. Sometimes I'll do 2 integers before I try a fraction. We're just trying to make sure we can find the answers as quickly as possible. So this is 6. That would be 2. This is 4. That would be -31. That's going to be -62, and that makes that -50. So notice that got further away. Now, because we have a lot of integers, I might try one more, positive one, before jumping into the fractions, just to see if I'm still getting further and further away from 0. So this is still 3, -4, -35, and 12. So this pulls down. This is 9. That would be 5. This is 15. So that's -20, and that's -60, which means that is -48. So coming closer back, so we might try 4 before we throw in the towel on the integers and then try a fraction, because I'm looking for something that's going to get me a 0. So then if we do 4, this would be 12, so that's 8. This would be 32, so that's -3, and that is -12, and we have found it. Okay, so what we know is that this factors into an x minus 4. That's what this guy is. And then this is reduced by 1 power. So this was an x to the third, so now it's an x squared. plus 8x minus 3. So that's what we've just done. We've factored that out. Now we want to try to solve this, but we want to try to solve it not using the synthetic division method because it's a quadratic. So you can either use quadratic formula or you can try and factor. If we do 3 times negative 3, that's negative 9. And if we use a negative 1 and a positive 9 as our factors, we, I think, can factor this without using quadratic formula. So we'll expand this to 4 terms. Pull out the 3x in the first pair. Pull out the negative 1 in the second pair. This is x minus 4, x plus 3, and 3x minus 1. So I now have a completely factored form of my equation, so that's equal to 0 like we were originally. So our solutions are 4, negative 3, and then we have to add 1 and divide by 3, so 1/3. All right, guys, I hope this was helpful for you studying for your final exam. I hope everyone does well, and let me know if you have any questions. You can comment on the YouTube channel, but also reach out to your actual instructor if you were taught it a different way or if they emphasize something more so that you can make sure you know what you need to do to get all of your points.